Okay, so dear, welcome back. So the other day we introduced you what is control, very basic. We have two types of control: open loop control, closed loop control, or feedback control. Okay, his other name is closed loop control. Okay. Because you see, closed loop control, because loop is closed here. Huh? So it's the open loop control, closed loop control, and sensing, acting, action rules. These are the basic components of a control which we discussed. And we also told you that today we will discuss more about second order system. Why second order system? If somebody asks you, because the actually the behavior of the second order system is very peculiar. And if we understand the behavior of a second order system very clearly, then we'll understand the control also very clearly, because many engineering system can be modeled as a second order system. Okay, and see, control only is relevant when there is a dynamics, right? That means something is moving and continuously with respect to time. You are trying to achieve something. So these are represented by dynamic equations. Okay, so second order system, as a name reveals, that are those systems which can be represented by second order differential equations. Okay, so examples of second order system. Examples are mass spring damper system, okay, and LRC circuit. So this is an example I have taken from mechanical engineering domain. This is an example I have taken from electrical engineering domain, but their modeling, their techniques are same, their mathematics is same. So we'll discuss uh, first mass spring damper system, because they are basically same. Their dynamics can be represented by second order linear differential equation. Let us see. First, slowly but steadily, we'll um, discuss all these simple but not so simple concepts. Okay. Say I have a mass hanging from here. This is a fixed wall hanging uh, by a spring, and through a spring and a damper having damping coefficient C, and the spring have a stiffness value K. And say we are considering a single degrees of freedom system, 1 degrees of freedom, okay, system. Meaning that, say, if this is my direction of motion, so this will be 1 degrees of freedom. That is x only, no x, y, or anything other than that. Okay, so this is single degrees of freedom system. That means the system can be represented by one parameter x. Okay, the motion of the system. Now let us see how I can formulate the dynamic equation of this system. And I like there are so many ways, you see, and basics. This is a spring constant we call, right? So suppose I am pulling it with some force F, okay, and then you see any mass is hanging, okay, and now I am pulling it with some force F. So F will be, and as a result of that, from here the mass is moving, okay, to this point. So this is the displacement. Say this is x. Okay, so single degrees of freedom, only x. So x will be k into x, right? So because that I have given some force. Now how much displacement this mass will undergo will depend on the nature of the spring, right? If it is very stiff, very small displacement. If it is sluggish, then large displacement for the same force. So you will see K is stiffness constant, which is a constant for a particular spring, and of course you already know. So if you are measuring force in Newton and x in meter, so Newton per meter is the unit of x. Similarly, say a mass is hanging through a damper. What is a damper? Damper is a device, you see, a mechanical device which always resists motion. You know, when we are young, we used to play football, and so there was a hand pump we used to give, right? And so pump is the best example of a damper. So when you push the piston inside the cylinder, some resistance will be there. When you pull, there will be also some resistance. Okay, so this is an example. Again, otherwise, so and the resistance is actually proportional to the. Here it was proportional to the displacement, and here it is proportional to the force. So force x dot dx dt. So dx dt, sorry, velocity. So dx dt, x dot is actually dx dt. Okay. So here it is, force is proportional to the displacement for spring. Okay, so spring constant was thus Newton per meter, and here the damping coefficient we call damping coefficient equals to this, and you know what will be the Newton. This is x dot meter Newton per, okay, Newton second per meter, Newton second per meter, isn't it? So F divided by, you see, meter per second. So second is going up. So this is the unit of damping coefficient. So these are very simple things which you should know. So let us now go further, discuss further. Okay. So this is a how it becomes a second order system. Let us try to understand. Okay. First, we will try to write down the free body diagram, draw the free body diagram of this system, right? So what is the system? Mass hanging through some spring and damper, and say I have applied a delta amount of force, and delta amount of force, small force, and duration say delta t time, very small duration, just like I give something like that. Okay, just hit impulse. Okay, just for the little force. So this is called perturbation. So I am perturbed. I am perturbation. Definition of this is delta amount of force acting on a system with a small duration, delta t, is called perturbation. So if I perturb, and then I would like to see how the system behaves, right? So what way it will behave, we'll try to do that. But before that, free body diagram, draw. And LRC circuit also, you see, is like this. If our so there is a source of EMF or battery or whatever, okay, and you see L, R, C, current will flow through the circuit once I just connect the two ends, okay, of the battery. And perturbation means I just connect and disconnect, because I am talking about understanding the system's behavior, okay, when it is free to oscillate. So we will discuss first free oscillation. That means I will either perturb in case of mechanical system, in case of electrical system, I will just energize the circuit with small time. Okay, I will just connect the two end of the battery and disconnect. Okay, and with the effect of that, how the system will behave is the domain of free oscillation. We are trying to take the example of this and draw the free body diagram first. So what are the forces? Free body diagram. Free body diagram of a mass spring damper system. So henceforth we will call it MSD. Okay. So you see, I have a mass here. Then free body diagram means I cut this part. This all the constraint. I am making the body free from all the constraint. Constraint was spring and the damper, and represent the constraint with respective force. So what are the forces? The when I perturb in this direction, so this is my direction of motion. Direction of motion. This is positive. This is positive. Okay. So when I perturb, that means I pull this body. This is my X. Okay. And I leave it. So what are the forces acting and what is the differential equation of motion? So all we are going to study now. So here is spring force Kx, and here is Cx dot, that is the damping force. Is there any other force? Yes, the only one force is actually inertial force, which is mass time acceleration, which is opposite to, so this is my direction of motion. Opposite to the direction of motion, I need to apply inertial force, which is mass time acceleration. And under these three forces, the body can be considered as a is in static equilibrium. So although pseudo bodies you can see should oscillate. If C is sufficiently small, it should oscillate. But as we are telling, with these forces, the body reaches to static equilibrium state. When it will reach to the virtual static equilibrium state? When you just apply on the body mass time acceleration in the direction opposite to the direction of motion. And what is that principle? Is very well known principle. Yes, you are right. It is known as, we have applied D'Alembert principle, very well known. So D'Alembert principle is a very powerful principle, and if you knew it before joining the entrance exam, maybe all dynamic problem you could resolve in the virtual static problem, and you could apply all static equilibrium conditions to solve those kind of problem, right? So is there any other force? No, there is no other force. So immediately you will see, whoa, what is gravity? We are considering free oscillation. So gravity has no role to play here. You see, even if gravity is there, you see, gravity will cancel out. I will show you. Now, concentrate here, right? So, what is the static equilibrium condition? The summation of all forces in case of planar force, summation of all forces in the vertical direction equals to 0. All forces means active force and reactive force. Okay. So, these are the two, all these are active forces. Okay. And active force and reactive force, summation of all this will be equal to 0 in vertical direction. In horizontal direction, also the summation of all the forces in the horizontal direction will be 0. And moment of all forces about a point will be 0. So these are the three conditions we can extract by considering a body is in static equilibrium state. Planar forces we are considering, okay, only. So these are the three conditions you have and three unknowns you can get. So these are all story of mechanics, you know. But here I only need one, that I am summing all the forces acting in the vertical direction equals to 0. Then what will be the dynamic equation? Mx double dot plus Cx dot plus Kx equal to 0. Because I have only perturbed the system. This is called free oscillation. Okay, I am assuming that there is no steady state force acting on that system. I have just perturbed, I have given this disturbance and I have left, okay, and then the body will oscillate following the oscillation will be governed by this differential equation. Yes, you are right. X dot means dx dt, x double dot means of course, right? So here, okay, so this is second order differential equation, okay? So wait a minute, this is called second order differential equation. We will discuss more about the nature of this second order equation. But now let us resolve. I told that free oscillation, gravity has no role to play here. So, but you see, somebody consider, no, the gravity is there. Let us consider that gravitational force also. So, according to you, then there will be a gravitational force. But then, what will be the inertial force? You see, inertial force was, according to D'Alembert principle, is a force which is mass time acceleration. Now, when we did not consider gravity, then the force was mass time acceleration only due to displacement. Now you are telling gravity is there. So, in this direction, there was acceleration due to displacement plus mg, okay. So, these are all now come up here, okay. So, this will be inertial force, and now let us see what you are getting here. Just I will tell you. You can also figure out plus Cx dot plus Kx equal to mg plus mg plus Cx dot plus Kx equal to mg. So this mg cancels out. So you have to believe me now that gravity in free oscillation, gravity has no role to play when we are trying to understand the body's motion. So what gravity role has? So gravity will actually determine the mean position of equilibrium about which the body will oscillate. That is the only role gravity will play. That means if I go to a place where gravity is very small, then say the m will be here. The mean position of equilibrium will be here. If somewhere I go where gravity is much higher, then the mean position of equilibrium when this will be there will be here. And earlier, say, body will oscillate about this mean position of equilibrium. Now it will oscillate about the mean position of this equilibrium. But nature of oscillation, this and this, will not change. Okay, so that's the clarification I wanted to make. So this is a second order system dynamics. Okay, second order system equation, right? Dynamic equation. And you see, this is many characteristics are there. Okay, number one, this is second order. Two is a linear. Second order linear time invariant time invariant system. So this is the characteristic of this system, which is second order linear time invariant. You can argue, oh my God, is the time varying with, the mass is varying with time. Okay, so if you just hang a mass with a spring, and you just in this direction you perturb, okay, delta f, delta t time, and don't you think this body will oscillate? If there is only spring, it will oscillate. The oscillation will be simple harmonic motion and it will oscillate forever. Okay. So it's varying with time, and I am telling time invariant system. Yes, the definition of time invariant system means if the, so now there are two types of parameter. If you see this equation, right? One x, which is called state, x dot is the derivative of the state, x double dot. So these are called state parameter. Okay, they are defining the state of the system. Another is system parameter, mass, K, C, damping coefficient, stiffness, spring stiffness. These are called system parameter. System parameter. So since our discussion will be limited to linear system now means that system parameter, you see, the time invariant means the system parameter, time invariant system means the system parameters will not vary with time. Mass should not vary with time, C should not vary with time, K should not vary with time. Then the modeling we are trying to do, the dynamics we are trying to understand will be completely different if we do not assume it's a time invariant system. For example, the mathematical formulation which we will do now cannot describe the time variant system, just like dynamics of a missile, for example. Is an example of time variant system. Why? Because the mass of that structure system changes with time. The moment huge fuel is burned, okay, and the mass is changing at the initial launch of the missile and final hit of the target, there will be substantial difference in mass. So we'll have to, if I try to control, that's why missile control is much more difficult than controlling a second order system like this. So step by step. So we are assuming our system here is time invariant system. Okay. So system parameter does not change with time. MCK does not change with time. That is the definition. Okay. Then, and this is a second order system because mass spring damper system is a second order system because it can be defined by a second order differential equation. Also, we will assume that this is a linear system. What is the meaning of that? Meaning is that, you see, by the way, solving, I need to solve this differential equation, and the solution is not so easy. Okay, so we'll try to see how to solve this kind of equation. But when I will get the solution, you will see, you will get two solutions. And if I do not assume the system is linear, then I cannot figure out the final solution. In this case, we will assume the system is linear so that as many solutions will be there. Here there will be two solutions. Okay, we'll discuss about that. Those solutions can be put together, superimposed, means add together to get a final solution. So this is the characteristic feature of a linear system. So today you have learned that what is a second order system, what is mass spring damper system, how mass spring damper system can be modeled by a differential equation, and then what is the characterization of this differential equation. It is second order, it is linear, it is time invariant, all kind of things are there. And then, as I told you that how to solve this kind of second order differential equation, linear differential equation, is of our interest. For free oscillation means here it is 0, you see. Only perturbation, that is negligible force is there. Okay, I can put it 0. So when I just perturb the system, how system will behave, that's our area of interest. Okay, and we'll continue our discussion in the next lecture starting from here. Till then, stay safe and have a nice day. Bye bye.